I am Geetha, working as an assistant professor in the Department of Mathematics, Vishayavar College, Trichy. Today I am going to talk about solving linear programming problems by graphical method using the software GeoGebra. Before going into the topic, we first learn about what is mean by linear programming problem, and then what is mean how to solve the linear programming using graphical method, and then how to use GeoGebra to solve this linear programming problem. A linear programming problem is an optimization problem in which the objective is to maximize or minimize a linear objective function subject to a set of linear constraints. These constraints represents the limitations or restrictions on the decision variables. And the linear programming problem consists of three sets of equations. One is an objective function, and another one is set of all constraints, and third one is an non-linear or non-negative restrictions. The objective function is a linear function that needs to maximized or minimized. It generally represents a goal such as profit, cost or production output. Example, maximization of z equal to 3x plus 4y, where z is an objective function. Number 2, the decision variable is most important. These decision variables are always non-negative. The decision variables, for example, in this objective function 3x plus 4y, x and y are known as decision variables. And the set of all constraints. Constraints is a set of all linear inequalities or equations that restricts the values of the decision variables. For example, the condition 2x plus y less than or equal to 8 and x plus y less than or equal to 6. That means the combination of decision variables is form an inequality or equality. And the next condition is a non-negative restriction. The decision variables are often restricted to be non-negative. The non-negative variables x and y are always positive. It is a simple example to construct or to explain or to learn about the linear programming problem. And the problem is a small company producing two products, product A and product B. Each unit of product A requires 2 hours of work, and each unit of product B requires 1 hour, and the company has a total of 6 hours available. That means the working time is 6 hours for production. Each unit of product A requires 1 unit of material, and each unit of product B requires 2 units of material. The company has 4 units of material available. Every day the company manufacturing material availability is only 4 units. Identify the number of products produced to maximize the profit. This is the problem. Now the problem is converted into a linear programming problem. First we have to decide what are the decision variable to construct a linear programming problem. For example, here the problem is an maximization problem because our aim is to improve the profit or getting more profit. Maximize the profit, z equal to 5x plus 4y. Here x is the number of units produced product A, and y is the number of units unit of product B produced. And the constraints are, here the two constraints are there. One is the depends on the time, and another one depends on the material. First constraint, which depends on the time constraints, each unit of product A requires 2 hours of work, and each unit of product B requires 1 hour. Therefore, the company has a total of 6 hours available for production. For that reason, we have 2x plus y less than or equal to 6, because here x denotes the number of products produced A and y denotes the number of products produced by P. And the product A requires for 2 hours. For that reason only we have to multiply this 2 and x here, and the product B requires only 1 hour. That's why its sum it as plus y only, and the total working time will be strictly less than or equal to 6, because the company has a total 6 hours of availability for production. The second constraint is material constraints, which depends on the material availability in the company. Each unit of product A requires 1 unit of material, and each unit of product B requires 2 units of material to produce that particular product, and Also we have a restriction on that. The company has 4 units of material available for the entire unit time. For that reason only the equation is like that, that is x plus 2y less than or equal to 4, because product A requires 1 unit of material and product B requires 2 unit of material, and the total availability is restricted to 4 units. For that reason only we have constructed this equation as x plus 2y less than or equal to 4. And the third condition is most important condition, which is the non-negative conditions, that is x greater than or equal to 0, y greater than or equal to 0. Always in the linear programming problem, we assume that the decision variable is always greater than or equal to 0. Here is also the variables x and y are greater than or equal to 0, because the number of units produced for the product B and product A is always positive. It never comes under negative constraints or 0, negative quantity, right? So the entire problem is look like that. First one is an maximization. This is an adjective function. Second is an second condition is an non-negative restrictions, and third one is an non-negative restriction. These three conditions are more essential to solve these linear programming problem. Different type of solutions are available for this linear programming problem. Number 1 is unfeasible solution. The feasible solution is one that satisfies all the constraints of the linear programming problem, including the non-negativity restrictions on the decision variables. It satisfies only the non-negative restrictions and the set of all constraints. Next one is an optimal solution. Optimal solution is a feasible solution. Also feasible solution which also satisfies the objective function. That means in an optimal solution it satisfies the non-negative restriction, the constraints, as well as in the objective function. This is known as optimal solution. And then infeasible solution. Infeasible solution is one that does not satisfy all the constraints of the linear equation. And unbounded solution. An unbounded solution occurs when the objective function can be made arbitrarily large in a maximization problem or arbitrarily small in a minimization problem without violating any constraints. And then the degenerate solution. The degenerate solution occurs when a feasible solution exists at a point where more than one necessary number of constraints are active satisfied with equality. Then it is known as degenerate solution. And then multiple optimum solutions. Multiple optimum solutions occurs when there is more than one feasible solution that provides the same optimal value of the objective function. Sometimes the optimal solutions, different combinations will give same optimum solution. At that time we represent the solution as multiple optimum solution. Here we have to learn about the graphical method to solve this linear programming problem. There are 4 steps to solve this linear programming using graphical method. Step 1 is plot the constraints, convert each the constraints into an equation if it is an inequality. Plot each constraints on the graph as a line. Suppose we convert it as an equation, then we can draw this as a line. Identify the feasible region, which is the area where all the constraints satisfied simultaneously. Number 2, identify the feasible region. The feasible region is the region where all the constraints overlap. The region is bounded by the lines representing the constraints. Evaluate the objective function at the corner points. The optimal function solution will always be at one of the vertices, corner points of the feasible region, and then calculate the value of the objective function at each corner points. Number 4, step 4 is choose the optimal solution. For a maximization problem, the optimal solution is the point where the objective function has the highest value. For a minimization problem, the optimum solution is the point where the objective function has a lowest value or the minimum value. There are 2 limitations for this graphical method. Number 1, it's only work for 2 variables for the problems. So, because we can draw a single line in the equation, we can mark it as a bounded region or a feasible region. if suppose it is a more than 2 variables, then we cannot draw a graph very easily. It is more complicated, right? For more variables, this method becomes impractical. It is a simple example to learn graphical method. The problem is maximization of z is 3x plus 4y. This is an objective function, and the restrictions are, and the inequalities are 2x plus y less than or equal to 6 and x plus 2y less than or equal to 6. These are all the constraints, and the condition x greater than or equal to 0, y greater than or equal to 0 are non-negative restrictions. In the step 1, we have to plot the entire equations into a line in this graph. This is a simple example to learn graphical method. This is a linear programming problem. Maximization of z equal to 3x plus 4y is an objective function, and 2x plus y less than or equal to 6 and x plus 2y less than or equal to 6 are all the constraints, and the condition x greater than or equal to 0, y greater than or equal to 0 are non-negative restrictions. In the graphical method, there are 4 methods, 4 steps are available. Number 1, plot the constraints. First constraint is 2x plus y less than or equal to 6. Convert this into an equality. It will become 2x plus y equal to 6. Suppose we plot this graph, we can find some points on this line and then draw the graph, which is more easier to draw. This gives 2 points 0, 6 and 3, 0. We plot it in the graph, then we get a line for 2x plus y equal to 6. Similar, the second constraint is x plus y less than or equal to 6. Convert this as an inequality, which is x plus 2y equal to 6, and the corresponding points are 0, 3 and 6, 0. And the third constraint is x greater than or equal to 0, y greater than or equal to 0. X greater than or equal to 0 and y greater than or equal to 0 means these are all the non-negative restrictions, mean which the entire solution lies in the first quadrant only, right? These represent the first quadrant where the box x and y are non-negative, right? Plot the feasible regions and then mark these points, feasible regions. Next we have to use GeoGebra to plot these lines and mark these feasible region and the corner points, and then we move on to the objective or optimization of the original problem. This is an GeoGebra window. You can use online mode online in the forum. Also we can use this GeoGebra Classic. Just enter this GeoGebra Classic on this Google Chrome page, then the window will be opened clearly. In this window, we can draw the entire 3 lines as a line. First, we have to draw the line x greater than or equal to 0, which is the first non-negative restriction, because the x greater than or equal to 0 means which lies in the right side of the y-axis, which is your x greater than or equal to 0. Similarly, your y greater than or equal to 0 portion is an upper side of the x equal to 0 x-axis. The both x greater than or equal to 0 and y greater than or equal to 0, which intersect here, which is shaded in the dark, you can easily visualize. And the third line is 2x plus y less than or equal to 6. This is a line 2x plus y less than or equal to 6. And the 2x plus y less than or equal to 6 means, and the entire portion lies below this line 2x plus y less than or equal to 6. These 3 conditions impose the feasible region is here, that is this entire triangle. Similar, the fourth condition is x plus 2y less than or equal to 6. This is the line x plus 2y less than or equal to 6, which is the shaded region is also below to the line 2x plus y less than or equal to 6, which this is noted as the line D, right? And the entire we can draw, now we draw the 4 lines into a single graph, and the shaded region or the feasible region is here, which is bounded by this line A, B and then CD. The point A, which is the intersection of line C and line D. Similar, the point D, which is the intersection of line B and then line D. Similar, the point C is the intersection of line A and line B, and the point B is the intersection of x-axis and the line C. This is your feasible region. That means your A, B, C, D, which is the feasible region. And the corner points in the graphical method, and the corner points will occur, and the corner points contains the maximization value or the objective values, or and the maximum value or the minimum value occurs at these corner points only, right? We have identified the 4 points A, B, C, D. The points are 0, 0, 3, 0, 2, 2 and the point 0, 3 which construct the feasible region. Now we have to maximize this objective function by constructing the equations. Calculate the objective function at each corner points. At the point 0, 0, the value of z is, at the point 0, 0, the value of z is 0, and at the point 3, 0, the value of z is 9, and at the point 2, 2, the value is 14, at the point 0, 3, the value of z is 12. Comparing these 4 values, that is 0, 9, 14 and 12, 14 is maximum. Therefore, the main linear programming problem has a maximum value at the point A, at the point 2, 2. Suppose it is a minimization problem, we can switch over this result to at the point 0, 0. The highest value z occurs at the point 2, 2 with z equal to 14. Thus, the optimum solution is x equal to 2 and y equal to, and the maximum value of z equal to 14. Similar, we can draw everywhere multiple number of constraints are drawn in the single graph, and then we can plot it. We can shade it in mark it as a feasible region. Then we can find the optimum solution for the linear programming problem. Thank you.